Okie dokie. We're done with this one. I'm going to close that. Don't save it. And there's my recording thing. And then I'm going to bring this one back over here and just drop that in and then make this one larger. And now we're going to go on and talk about normal probability distribution. And we'll do it. That's interesting stuff. We'll do, I'm getting a little bit tired. We'll do, go through the theory here, and then we'll do an example of normal probability after this one. So the normal probability distribution is the most common distribution for describing a continuous random variable. So that's really good to know. This is the most common one. Normal probability distribution looks like this. So I'm just going to bring this over here and put it onto the one that we're talking about. And I'll put that right there and just, it's this bell-shaped curve, right? And it is widely used in statistical inference. So remember, statistical inference is that we have a population, which is everybody. So the population of all the students at City College, that's the population, right? It's a population. And we could, instead of measuring something about all of every single student and having to get data on every single student, we could take a sample from the population, and then we could measure that sample, and then we can make inferences based upon that sample. We can make inferences about the population. That's statistical inference. And the normal probability distribution is widely used in statistical inference. It has been used in a wide variety of applications, including heights of people, test scores, rainfall, scientific measurements, and this is where it came from. The normal probability density function, so we'll just keep this here just as a reminder of the kind of shape we're dealing with here, and I'll make it a little bit smaller. I'll actually put it over on this side just because. There we go. Here's the normal probability density function, and so it's the function that we use, and we've got u, the mu is the mean, and x is the value we're looking for, right? So like, hey, we want to know the flight time, the probability that the flight time is between a certain range, or that somebody's height is between a certain range. So this is the probability density function. And we have the standard deviation here, and we have pi, and we have e. And so it's a pretty complicated looking formula, but actually working with this isn't that complicated. Distribution is also symmetric, so I'm going to just grab this from here and copy it and put it here. And you can see it's symmetric, right? It's like, here's the middle, and it's the same on the left and the right. There's no skewness. So for a normal probability distribution, there's no skewness. And the entire family of normal probability distributions is defined by its mean and its standard deviation. Okay, and so we're going to see how that defines this normal probability distribution. And so the highest point of the curve is its mean, and the mean is also the median and the mode. And that's right in the middle. Okay, and it's symmetrical on both sides. It's not skewed. So that's how the mean is helping define a normal probability density, normal probability distribution. The mean is helping define that. And then the median and the mode, incidentally, are the same as the mean in a normal probability distribution. I keep wanting to say density. The mean can be any numerical value, negative, 0, or positive. So, on a line, it could be, the mean could be anywhere there. And then the standard deviation, again, we're learning how the mean and the standard deviation define the normal probability distribution. Standard deviation determines how wide or how narrow, how steep the normal distribution is. And so you can see this here. Larger values of a standard deviation result in wider, flatter curves. Because if this is the mean and we have larger standard deviations, we're going to have data further out. And if we have narrower standard deviations, our data is going to be more clustered around the mean. And so you could see this here. It's a narrower standard deviation, smaller standard deviation. So the data is more closely clustered around the mean. And here, it's a wider standard deviation, a larger standard deviation. So the data is more dispersed around the mean. So you get a wider normal distribution. And probabilities for the normal random variable are given by areas under the curve. So again, we're talking about area as a measure of probability. And we saw that when we were talking about the uniform probability distribution, right? But here we're talking about the normal probability distribution, this bell-shaped curve. And the total area under the curve is 1. And it's 0.5 to the left of the mean and 0.5 to the right of the mean. So half your data is on the left of the mean, half your data is on the right of the mean. And then finally, we could, there's characteristics of the normal probability distribution. This is the basis for the empirical rule, the 99.7, 99, 95, 68 rule. And that's that 99.7% of your data will be within three standard deviations, and 95.4% will be within two standard deviations, and 68.3% will be within one standard deviation. So we'll see an example how to use this in the next video. See you in the next video.